So, welcome to my talk, Interactive GPU Programming with ClojureCUDA and ClojureCL. My name is Dragan Djuric. I'm a professor of software engineering at University of Belgrade. And I have been using Clojure for almost a decade now. And I have some interesting projects. I hope that they will be interesting to you. You can find my contacts online. All code is on GitHub. There is documentation at uncomplicated.org. And also I have lots of tutorials at dragan.rocks. So you can find, if you're interested in this, you can learn it by some beginners tutorials, some intermediate tutorials, some advanced tutorials. So, functional programming is great. I hope we all agree on that here. So I will not spend much time on it. I will talk about some data processing and not necessarily big data. The thing is, even if we have a small amount of data, we may need lots and lots of computations. And usually in this area that I'm talking about, this means that we have numerical data, large arrays, and we have some numerical algorithms to just compute it lots of times. And functional programming is unfortunately not very good at it. I mean, it's maybe not bad, but compared to some state-of-the-art software that is available, for example, NVIDIA's CUDA libraries or Intel's optimized libraries. Actually, when we program something using functional programming languages, it's not even close in that area. So it's a bit of a problem. But on the other hand, functional programming is really nice to be used, even in numerical algorithms. So my idea and what I do with these libraries is to bring as much as I can of the performance of these numerical heavy libraries to functional programming world, and specifically to Clojure and Java Virtual Machine. On the other hand, CPU is not really great at number crunching because there is lots of hardware in the CPU that is not really dedicated in efficiently crunching numbers, but to other things. And some programmings that are usually used in number crunching, such as Python, for example, these languages are not really great at it. They just use optimized libraries in a nice way. And if we tried to program this in plain C, it's also a problem because portable C is not really great at number crunching. Actually, we have to create really hardware-specific code if we want to get good performance. And this is a place for GPUs, because GPUs contain very simple computing units, but there are lots of these units. And actually these features that these units have are actually exactly those features that we need in many number crunching algorithms. So that's why GPUs are really successful in machine learning and in high performance computing. And they get faster and cheaper each year. That's also a great thing. So for a price of one gamer GPU, let's say 500 or 1,000 euros, we can get power of 10 CPUs. If properly applied. But on the other hand, the biggest problem is that these GPUs are really, really hard to program, and programming tools are really from the Stone Age practically. And that's why I create some libraries to help us with this. So Uncomplicate is a family of Clojure libraries for number crunching and data analysis. You see that ClojureCL is a library that enables OpenCL in Clojure, and with full speed and practically no overhead over the native C interface. Also, ClojureCUDA is the same, but for NVIDIA's proprietary CUDA platform. So you can use basically whatever you would program in C++, you can also do in Clojure, most of it, without any noticeable decrease in performance or overhead, but with much nicer interface. And what is really important, in a dynamic interactive REPL. So you get a console, you don't have to deal with a complicated C++ tool chain or to recompile your program each time you change anything, but you can have an interactive console, Clojure REPL, and just write your code there and see the results right away, and learn CUDA or OpenCL in a much easier way than is normal with C++. And then I use these libraries for Neanderthal, which is a high-level optimized linear algebra and vectorization library for Clojure. And it supports transparently either CPU via Intel's MKL libraries, which are really optimized for CPU computations. And also it supports both NVIDIA's CUDA and OpenCL on all major three platforms. So NVIDIA, AMD, and Intel's platforms are supported. And everything is transparent and accessible from Clojure and integrates well into Clojure workflow. And Bayadera goes a step further. This is a Bayesian data analysis library. And it doesn't only integrates existing optimized libraries, but has lots of, let's say, custom code, which really integrates Neanderthal. It supports CUDA and it supports ClojureCL. And it's a showcase of how you can use this stuff to program your own algorithms. So basically, if we can describe our algorithm with linear algebra, we can use Neanderthal. But then, of course, in many cases, our algorithm is special in some way, so we have to write something on our own. In that case, we can use ClojureCL or ClojureCUDA to write the missing parts in a nice way. So Bayadera does that. So let's start with a hello world. I want to show you first how it looks like when you use this stuff. And for number crunching, dot product is really one of the simplest building block of more complex algorithms. And it's also nice because it consists of two familiar functional programming idioms, map and reduce. So to compute a dot product of two vectors represented as arrays, first you would have to map the multiplication operation over these two, and then to reduce them with to sum all numbers, you get one number that represents a dot product. So in idiomatic Clojure, this would be the code. So you see the function is implemented with one line of code, and then used like an ordinary function call. Here is the result, which is not really important, but what is important is that on my desktop, which is maybe 4 years old, it takes 14 milliseconds to compute a dot product of two vectors of 100,000 elements. So it's not that much data, but it's not a small vector either. So 14 milliseconds. It seems fast, But on the other hand, we almost never need to compute a dot product on itself. The point is, it is one small building block of a larger algorithm. So we would have to do lots of these dot products to get any meaningful results that we are interested in. But okay, let's see, 14 milliseconds, and with Neanderthal, we have a dot function, so we don't have to write our own implementation, of course. And for the same size of the vectors, on my machine it's 4 microseconds for this size of data, which is some 3 orders of magnitude faster on the same hardware. And of course, we don't have to write our own implementation. We have these functions ready for us. So the next step would be, okay, but we've heard that GPUs are even faster than CPUs. So the same thing on the GPU, and it's 26 microseconds. So it's fast, but slower than on the CPU. And what was the problem here? What's the challenge? Let's see, before I tell you why is that, let's see a bit more complex example. Matrix multiplication, which is also common in numerical computing. So I have 2 matrices here, matrices X and Y, and both are 1,000 times 100,000 elements, and its result is 1,000 times 1,000 matrix. So basically, the resulting matrix has 1 million elements, and each element is computed by computing a dot product between the corresponding row and the column. So for this result, I actually need to compute 1 million dot products. So for 1 million dot products of the same size as before, it would be 23 milliseconds. So if we recompute that, it would mean that we spent 23 nanoseconds per 100,000 dot product, which is, we started from 14 milliseconds, so it's 600,000 times difference. Of course, and this is 3 orders of magnitude faster than the same computation, the same hardware, but a solo dot product instead of 1 million dot products in bulk. So the moral of this story is actually that whenever we have bulk data to compute, it pays off to put it on the GPU. If you only have single isolated operations, then maybe you could get good results, but often you would get a slowdown. So we have to have a problem that is big enough for GPUs to really see the speed ups. Okay, so when we have seen the hello world, let's see how we can write something of our some algorithms on our own. First, ClojureCUDA API. This presentation has been generated automatically from org mode. So actually, this is a session that I typed in REPL. So we can initialize CUDA. We can get some information. For example, see how many devices. On my computer, I had 2 NVIDIA cards. We can get a handle of a specific hardware, in this case, the first GPU. And the simplest thing is we can query some information to see what does it support. And in this case, I would get a Clojure map with lots of info. And from this info is important because then we can see what is the capability of the hardware, and we can optimize the algorithm in software, just in runtime to better apply it to the GPU. at hand. In this case, my device is GTX 1080 with 11 gigabytes of memory of RAM and 28 physical cores, and each core is capable of executing 1024 parallel threads. So some typical information you would find here that would be useful in your programs. But then the actual computation would be done in some context. Actually, in the context, we can set up the hardware that we previously accessed with the right parameters that we want to use. So in this case, I can also get a hold of the context and get some info and do some other typical CUDA API calls, but interactively in a REPL. It's not so interesting, but now we will get to some interesting stuff. Actually, modern GPUs usually have separate memory area. So first thing is I can instantiate, reserve some memory on the GPU where my data will be and where my computation will store some results. And these are numerical arrays typically, like row arrays. And of course, I get the reference in Java virtual machine that I can use to call some API on these arrays. And here I create a Java float array with the actual data that I will use to compute. So now I have two memory spaces. One is my main memory, one is my GPU memory. And the first thing that I have to do is I have to transfer data from the main memory to the GPU memory where the computation will be happening. So this is one function, mcCPU host, that will find the way how to do this in the best way. And I get the opportunity now to use this array. But I cannot access each element on its own. I just can access the whole array. So to check whether my transfer was successful, I can here transfer the data back to another array in main memory and see that the data is actually 0, 1, 3, 2, 3. So, okay, the transfer was correct, and then I can actually compute something already. The only C code that you would have to write here is the kernel code. Actually, I could have created a Clojure library for translating Clojure code to kernels, but I think it would do more harm than good, because this is only a tiny subset of C99, and it's really a good match to the hardware and good match to the problems. So Lisp code wouldn't be much easier here, and I wouldn't be able to use all Lisp dynamicity there, because GPU hardware is not really good match to that kind of computations. So I have to do static numerical computations, and C is really good at it, and it's only a small part of code is written in this way. But anyway, when I load it, either from a separate file or just a string that I can generate programmatically in whichever way I feel like, then I can use dynamic function calls to compile it, to create modules, to do all other stuff that I would have to do with C++ toolchain. So in this case, I loaded the kernel, I created a CUDA model, and I created a function, and now, finally, I can launch this function increment on a grid of 256 parallel processors, and I give the GPU data, array data as a parameter. And then I take the data back to the CPU, to the main memory, and I see that the data have been incremented. And it seems as a lot like there's a lot of work here. But the point is, with Clojure, I don't have to write this all steps. These were like all small steps to show you how it looks like on the small level, and also on the low level, and also to show you that whatever you can do in CUDA, you can actually do the same thing in Clojure, but in a dynamic interactive REPL with a nicer API. But of course, you would use all functional programming Lisp goodness of Clojure to make this much easier, which I will show you with Bayadera. So I don't know how many of you have any idea what is Bayesian data processing and what is the thing with Bayesian data analysis. But the point is, when it's useful when we have only a tiny amount of data and we have some prior knowledge and we want to mix it in a specific formal way to get the final updated predictions. So basically, this is how scientific process works, right? We have some hypothesis. We can, by studying the literature or whatever prior knowledge we have, conclude that there are some different probabilities of all these hypotheses. There could be infinite number of hypotheses. And then we create some experiments, gather some evidence, see the probability of all that data happening. We can define the likelihood of data happening if each hypothesis were true. And then we can use all this to get the final posterior probability, which is actually, you see in this formula down there. We are interested in probability of each hypothesis being true if the data happened. But we, of course, cannot measure this directly. But we can compute it from the opposite stuff. Okay, so simple enough and intuitive enough and conceptually really simple and really easy to understand. But the problem is real models are not so good fittings, so we cannot typically create a formula to compute this mathematically to give us the straight answer. We have to calculate this by numeric simulation. And the main algorithm family is Markov chain Monte Carlo sampling. So how does it work? It explores the hyperspace of many dimensions, just really trying different places and seeing whether there is something there. So basically, you have to try many places in this hyperspace to create a good representation, a good map of that space, and see whether in this space are some higher grounds where there is something. And typically, even for simpler problems, it is many minutes or hours or days even, or weeks. So naturally, GPU would be a great help there. But the challenge is MCMC is a sequential algorithm in its nature. So it's difficult to parallelize it. And if you want to know more about Bayesian data analysis, this is a really great book. Doing Bayesian data analysis by John Kruschke. It's really a practical book, self-contained, and all examples are really from the real data analysis. So it's really practical. It's not all theory and everything, but practical data analysis. So one real-world problem from social sciences would be typically having several hundred of measurements. In this case, we are trying to do some linear regression between human height and human weight. So naturally, taller people are usually more heavy, but not always. But we understand that there is some correlation. So typically, a regression line would stand like here, like this. The thing is that one line is not really great representation of all these dots. You see all these black dots. One line wouldn't represent them equally well. Bayesian analysis offers the distribution of probabilities of all possible lines that could be describing data. And not only lines, but all these variability across, around these lines. So instead of as ordinary frequentist linear regression that would give the best line, Bayesian data analysis says, okay, there is no one best line, all lines are wrong in some way, but let's have probabilities of all lines. That's the idea. But to do that, we would have to explore the whole space, and usually we can create hierarchical models. We are interested in y, it's the weight, x is height, and beta 0 and beta 1 are the parameters, regression coefficients. So basically, instead of getting one number for beta 0, one number for beta 1, like in regression, we want to get the whole distribution of beta 0 and whole distribution of beta 1 and whole distribution of these parameters for variability around it. So basically, we end up with 4 dimensions and 7 parameters of this hyperspace. This is the example from Kruške's book. And for this example, Kruške got this result. So we simulate this process and we get these rough histograms, the whole distributions. You see here that we have a distribution for beta 0, distribution for beta 1. So for example, for beta 0, the most likely it's around minus 150, but it also minus 190 also have some probability. So we can get this high dimension interval with 95 or 89 or whatever number we pick. 95 is just out of the blue. It's not some rule that you have to use. So we can conclude something about these numbers. And for this analysis, the state-of-the-art software scan took several hundred seconds on my computer. So how to do it in Bayadera? This is Clojure REPL. I can write some small amount of C code to describe the likelihood and prior. But then I can load this code and create a distribution, use some ready-made code from Bayadera, and everything will be automatic. So let me show you. This is model's prior function. You see it's some really simple C. It's not some complicated code. You can recognize all these 4 distributions from the previous slide. From this slide, you see 2 normal distribution, 1 exponential, 1 uniform. I use this here to just specify how the prior function should be computed on the GPU in the kernel. Likelihood is a bit more complex, but still, I only have 1 loop computing this posterior for all 300 data points. Also, not some heavy or complicated C, just something that any competent programmer can quickly learn. And then I can dynamically run it even though it's on GPU, everything would be compiled dynamically without any user intervention. Everything is dynamic, everything can be stored for later, tried with different parameters, and this is the whole analysis here. Even though it's on the GPU, it's less code than Stan on the CPU, or the comparable amount of code. It's not, and there is nothing GPU specific that user would have to write. That's the point. And these are the results. I don't know whether you can see it because the light is really bright, but the point is these are histograms. These are not these are actual histograms that I can get with Bayadera are so fine that these look like lines that were interpolated, but these are really histograms. So you get really fine answers, and this is actually the main point: how fast is it? So for this particular example, I used my old GPU. I did it in OpenCL. And on my 4 or 5 year old AMD GPU, I took 61 million samples in 267 milliseconds. And with my newer NVIDIA GPU, it could be 120 milliseconds or so. So this is, in this case, a couple of nanoseconds per a computationally heavy sample. And at the end, I get really precise, fine-grained histogram as the answer. But with JAGs or Stan, which are state-of-the-art C++ tools, it's for 20,000 samples, they took a couple of hundreds seconds, and the answer is a rough histogram because there are not so many samples there. So if we compared apples to oranges, I could say that Bayadera was a couple of million times faster. But of course, it's not really fair because they are using a more complex MCMC variant. So you could say that Bayadera's samples are a bit more naive. But on the other hand, I can take much more samples to alleviate that problem. So in apples to apples comparison, which is, okay, how long does it take to complete the whole analysis, Bayadera was 1,000 times faster, which is considerable. Why is it considerable? I mean, both are fast. But the thing is, something that is 1,000 times faster means instead of 1 second, it would have been 1 hour with a slower method. So instead of several days, it would be 1 minute, or instead of a couple of months, it would be 1 hour. That's when it's important to have something really faster. Something that is, let's say, 1 microsecond instead of 1 millisecond, okay, it's not really important because 1 millisecond is fast enough for a human. But when you have lots of things, then 1 second instead of a couple of hours, it's really pays off. So that would be at the end of my talk. Thank you very much. And before I take any questions, a couple of weeks ago, I started accepting donations, so you can adopt a pet function and support this open source work. So to repeat, there is a blog with lots of tutorials. There is documentation at uncomplicated.org, and of course at GitHub you can find the source code, and if you're interested to see how it's done. So thank you very much. I hope you have questions, or many of them. I love answering questions about these things. So please.
So we just got 5 minutes for questions. Swear.
I was just, you talked to us about the results of being able to do these computations on GPUs, which is profound, but I was interested in how you found it from a programming perspective, because GPUs aren't necessarily created and presented with what you're doing in mind, and I'm curious how that feels.
Yeah, the thing is, if I understood the questions right, so what is my feeling about how hard is it to program, or how enjoyable, or how it's a good fit?
Well, yes, and particularly, I mean, GPUs were developed for games and so on, and so it's interesting the way that now they're being adopted to solve all kinds of tasks that have nothing to do with games. But I'm curious whether, as a programmer, you find that taking them in that direction might be a less well-traveled path than people who are just shifting polygons around.
Oh yeah, I mean, it's not that unusual now. Lots of people use GPUs for just scientific computing, so there are algorithms developed. You can find solutions to many interesting problems. The thing is that usually the algorithm that was developed for CPU would not work on GPU or not work well. So you would have to develop your own variant or find some other solution. So there's lots of creative works even in solving, even in doing problems that are solved on the CPU. To get them well on the GPU, it's another research problem often, but it's what makes it interesting.
Okay, so it's more about you needing to shift to think about different algorithms more than prompted by the different platform.
Yeah, you have to think about in a massive parallel way, because to use GPU means using many different parallel hardware-enabled threads, basically. So it's programmed in a different way, but luckily I am in my libraries I try to create some generic code that can help with this also. So for programmers that are coming from functional background, to have an easier transfer path, but still get the optimal performance.
Sure. Thank you, Dragan.
Yeah.
Okay. You got any more questions?
Thank you. That was a great presentation. Question: you mentioned that the small C snippet that you had in your Clojure code in a constant, that was just a demonstration. I assume that you've made some macros to generate the C code there in real life, or you still write the C code?
No. The thing is, I could have made some macros to help me with generating them programmatically. But the thing is, these C snippets are called kernels. Like, kernel is a function that really runs on the GPU. These are usually not that complex. Most of the complexity is in the host code on the CPU, in setting up the computation and memory and all transfers and how the order of computation is done and everything else. So the thing is, most of the complexity is on the host when I am doing it with Clojure already, so it's much easier. And then these snippets are really well match the problem. So all the literature you see is in C. All the things that you can do, like the actual C extensions for CUDA or OpenCL are in C. So basically your Clojure code would not be much easier than this. And it would involve some complexity in translating and generating and everything else. So if you get some error in your kernel by writing it, you would have to think, oh, this is generated in this way. How I do it in real life, I write these C kernels in files, like ordinary C code, with syntax coloring and all the help from Emacs, and then I load it dynamically and do everything else in interactive way. Whenever I change a C file, I can just recompile it in the same REPL and get the continue computations. And so that's what I find as a programmer. I made this as a practical tool, not as a research tool. So my main goal is to enable really comfortable programming, not to write a paper or something like that.
Do we have any more? All right.
Yeah. I was wondering, have you experimented with dynamic parallelism?
Yeah. I use it in Bayadera, both in OpenCL too and on CUDA engine, because Bayadera also supports both OpenCL and CUDA, which is unusual in this world. Usually most libraries support just CUDA, and that's it. All my libraries support both CUDA and OpenCL transparently. And I use dynamic parallelism and it works, and I didn't have any major problems once you learn how to use it, of course.
Okay, how do you configure it from a kernel to launch another kernel, let's say?
Well, it's CUDA kernel.
How does it interface with the libraries that you have?
Well, there are no issues with the library because if you use dynamic parallelism, you're enqueuing the kernel or launching the kernels from the kernel. So it's ordinary C or CUDA code.
Okay, fair enough.
If you want to enqueue it from the host, then you would do it from with Clojure. So there is no mismatch there. So I didn't have any special problems with it. That's the main point. I make this as a practical tool. So I tried myself many times to get it right. So.
Thanks.
Excellent. Okay, I think we're just done with questions. So we're going to lunch now, to break. And a warm hand of applause, and thank you very much.
Thank you.